Okay, good morning. So what we were doing last time is we were looking at the stability analysis for heat equation, right. We were doing the linearized stability analysis for heat equation. To remind you as to why we were doing that, I had suggested that FTCS was unstable because the second derivative term that showed up in the modified equation for FTCS had the wrong sign, was negative, right. The coefficient for the second derivative was negative, right, and I had suggested that we could add artificial dissipation of our own, right. We could just add the second derivative term and try to knock out that negative term, possibly make it even positive. Okay, that was the suggestion. And then I had sort of casually mentioned that, oh, you can add as much dissipation as you want, you can add as much artificial dissipation as you want. Okay, that is fine. So, right, so what we are looking at now is what is the effect of this artificial dissipation. So if you add this if you can add as much as you want, right, then we had concluded that the equation with that much artificial dissipation was almost like heat equation. If you added an enormous amount of artificial dissipation, that was like heat equation, and was there a consequence to that. So we are just looking at the stability analysis of heat equation. We had already done it, right. I will just quickly repeat it. So what did we have? The heat equation, 1D heat equation looks like that. If you use FTCS, if you apply FTCS to this, again the problem by itself is not complete, right. I mean, you have to apply the boundary, I have to tell you what are the boundary conditions, what is the actual physical problem that we are solving. But since this stability analysis, von Neumann stability analysis is only at a grid point, right, we can just discretize this and answer that question. So FTCS applied to this is UPQ plus 1 is UPQ plus I will say lambda times UP plus 1 Q minus 2 UPQ plus UP minus 1 Q, where lambda is kappa delta T by delta x squared. Okay, and when we went through the same process, of writing UP plus 1 Q as e power in delta x UPQ. Incidentally, in some books you will see this called the shift operator because it shifts us by one grid point. Okay, so some books you may see this called the shift operator. Okay, so doing this, what did we get? We got UP plus 1, UPQ plus 1 divided by UPQ, which is G, the gain, what did this work out to be? 1 plus 2 lambda times cos theta minus 1, and we wanted the modulus of this to be less than 1, and therefore we got the condition that 0 less than lambda less than 1/2. Is that fine? That is 0 less than kappa delta T by delta x squared less than 1/2. So if kappa is very large, so the question is what dominates? What was the CFL condition, the regular condition that we call the CFL condition? That was 0 less than a delta T by delta x less than 1. Okay, and depending on the relative magnitudes of A and kappa, you will end up applying the appropriate stability condition. So if you make your artificial dissipation for the heat equation, it's kappa, but if you add it as artificial dissipation, it would be mu2. If you make the artificial dissipation too large, so large that mu2 dominates, for all practical purposes it becomes like heat equation, then this is really the stability condition that you need to be worried about. Okay, So if A is of the order of 1 and kappa is of the order of 1 million, then this is really the stability condition that you have to be bothered about. Fine, okay. Of course, in general you could say that it seems that the general scheme, general explicit scheme, right, using 3 points seems to be of the form UPQ plus 1 is some A times UP cube UP plus 1 Q plus B times UPQ plus C times UP minus 1 Q. Am I making sense? In general, an explicit scheme involving the points P plus 1, P minus 1 would look something like this. Okay, maybe what you can do is you can just try out, see how you do the stability analysis for this. Just substitute, go through the same process, just go through the same process, and you will see that you can come up with a stability condition in terms of A, B and C. Okay, you can make a general statement, you can come up with a stability condition in terms of A, B and C. You can try it out. If you have any difficulties, get back to me. Is that right? Okay, so this is as far as the 1D heat equation is concerned. So you can add artificial dissipation. You have to be very careful how much artificial dissipation that you add, right, you can't add too much of it. The other thing that you want to remember is the artificial dissipation term that you are going to add, to the equation that you are solving. That is, if the equation way back when I told you that u was a perturbation, but we will go back to a situation where u is the variable that you are solving for. So if the equation that you are solving is A dou u dou t plus A dou u dou x, and you want this to be equal to 0, but instead of 0 you are going to solve this. You are clearly not solving the equation that you set out to solve. Okay, you are clearly not. So it is not as though you are doing FTBS setting sigma equals 1, right. So the solution is contaminated. So from your point of view, you want to keep mu2 as small as possible. Is that fine? Okay. So and we rationalize this, we justified this saying anyway I am solving the modified equation, right. So I am just fixing the modified equation to my satisfaction. So this term possibly can be picked exactly from the modified equation. So when I do a demonstration, I will actually show you how to pick this, right, how we would pick this term. We will try out a few things and see what it does to the modified equation. Okay. So in a later class I will actually do a demo of deriving the modified equation, but in a automated fashion, and then we will see whether we can add different terms and see what that does. Okay, right. In this conversation I am going to do a little aside now. We are going to take a step aside, right, because I am with heat equation. I am going to continue with heat equation just for a brief period, right, and then we will come back to this conversation, right. I want to look at 2D heat equation simply because of the stability condition that I have got, right, simply because of the nature of the stability condition that I have got. I am going to make a point, I am going to use it to make a point. I want to look at 2D heat equation. 2D heat equation is dou u dou t equals kappa dou squared u dou x squared plus dou squared u dou y squared. It is an isotropic material, so kappa, there is only one thermal conductivity, right. Thermal conductivity is not changing based on orientation. Okay. So if I did FTCS for this, what would I get? So now I will use the superscript for time because otherwise I will have too many subscripts in the denominator. I will use P and R for x and y, and that is q plus 1. Okay, q is in time, this is along x, that is along y, UPRQ, fine, plus lambda x UP plus 1 RQ minus 2 UPRQ plus UP minus 1 RQ. plus lambda sub y upr plus 1 q minus 2 upr q plus upr minus 1 q, where lambda x is kappa delta t by delta x squared, lambda y is kappa delta t by delta y squared. So, to keep life simple, I am going to make delta x equals delta y equals h. Okay. So, I can then combine these. So, what does this give me? UPR q plus 1 equals all of this. I am going to now do the same thing that I did for in the 2D case, what I did for the in the 1D case, right. So, I do not know whether I can, if I just write it out, whether it is going to be a hassle for you. So, this is UPR q, maybe I do not skip a step, plus lambda times, what is this going to be? Remember delta x and delta y are the same, right. So, in delta x, right, you will have in delta x and im delta y, okay, in h and im y. So, that is going to give you 2 sets of thetas, okay. Maybe I will just write it out and then I will explain what I am doing. So, this will give me a e power I theta minus 2 plus e power minus I theta times UPR cube, and the other one will give me a lambda e power I alpha minus 2 plus e power minus I alpha UPR cube, where theta is n delta x and alpha is m delta y, but we have decided delta x equals delta y, but the wave numbers are still different, okay. However much we simplify, the x and y coordinates keep on falling apart, it does not matter, okay. So, what does it give me? Therefore, the gain when you take one time step, what is the gain? 1 plus is going to be very similar to what we had earlier, 2 lambda cos theta minus 1 plus 2 lambda cos alpha minus 1, okay. And when is mod g less than 1? When is mod g less than 1? So, you can combine these two basically, right, when because you basically have to look at when these values are the largest. So, that will correspond, I will let you work that out, that will correspond to 0 less than lambda less than 1 by 4, okay. Just like we did in last class, you can just work out mod g less than 1 and you will see this is the condition that we get, right, and we can sort of guess that if it were 3D Laplace equation, it will be 0 less than lambda less than 1/6, okay, you will just get one extra term for the z coordinate, okay, right. But this is really what I was interested in, this condition. When I saw the 1/2, I said okay, let's take an aside and look at. So, lambda equals 1/4, what happens here when lambda is 1/4, what happens to this equation when lambda is 1/4? What happens to that equation when lambda is 1/4? When lambda is 1/4, you get a very familiar looking equation. UPR q plus 1 is 1/4 UPR q plus t plus 1 r q up minus 1 r q plus minus 4, is that right? That gets cancelled, plus up r plus 1 q plus up r minus 1 q, right, which was our iterative solution to Laplace's equation. Fine, this is an iterative solution to Laplace's equation. We'll revisit this. I couldn't resist taking this aside. We'll revisit this later. But what this basically says is marching heat equation in time is the same as sweeping Laplace's equation in space. Okay, so now there are two different ways by which we can get solutions to Laplace equation. Either you take Laplace's equation, add a time derivative and solve the unsteady equation and allow this solution to evolve in time, or you do an iterative method, Gauss-Seidel or whatever it is, or Gauss-Jordan, and if you are doing Jacobi iteration, not Gauss-Jordan, if you are doing Jacobi iteration, it looks like all you are doing is solving heat equation. What if lambda instead of being 1/4 were 1/8? What would you get? Can you guess? Lambda instead of being 1/4, if I take lambda equals 1/8, what would you get? That is like picking some kind of a relaxation parameter. Anyway, if you want we can have this, as I said, if you want we can have this conversation later, but that is like picking a relaxation parameter. So you see, if you have UPR q plus 1, if you picked it as 1/8, right, you would get a linear combination of UPR at q, right, omega times that and 1 minus omega times that, whichever way you want it. You would get a linear combination, okay, you would get a linear combination. The only constraint that you have is that you have a stability condition here, okay, you have a stability condition here. Maybe I can work it out instead of, since I have gone down this path, maybe I can just work it out. What happens when lambda is 1/8? What do we get from that equation? Can you just tell me? UPR q plus 1 equals UPR q, lambda is 1/8, maybe you can just read it out, that is plus 1/8 UP plus 1 R q minus 2 UPR q plus UP minus 1 R q plus 1/8 UP R plus 1 q minus 2 UPR q plus UP R minus 1 q. Okay, there are 4 of these, therefore it becomes half. So that becomes 1/2 UPR q plus 1/2 UP plus 1 R q plus UP minus 1 R q plus UP R plus 1 q plus UP R minus 1 q divided by 4. So the 1/8 I have written it as an average plus 1/2. This is like taking omega equals half. Okay, I do not know how many of you tried when I said why do not you try SOR with Jacobi. I do not know if you have tried it. Did you try SOR with Jacobi? Anyone? Well, if you have tried it, you would have found that for omega greater than 1 it would not have worked, right. It would not work because for Jacobi iteration you have a stability condition that says lambda has to be less than 1/4, that is omega can only be at the most 1. Fine, Gauss-Seidel it can go up to 2, Jacobi it can't. Jacobi there is a stability condition that says that lambda is less than 1/4 or which corresponds to omega equals 1, okay. If lambda is greater than 1/4 you will not get the average, right, and it will not work, fine, okay. right. So this sort of connects, I wanted to connect what we were doing with Laplace's equation, right, with all this evolving in time. I want you to understand that, so marching in time to a steady state solution is the same as sweeping in space. So there is no sense getting worked up saying that, oh, you are going evolving in time, I am just doing sweeping in space, I am not, you have an extra coordinate, I do not have that coordinate. No, they are both basically the same, right, but what it does is it gives you a different perspective. The same algorithm, it gives you a different way of looking at it. So as long as you keep that in mind, that whether I am marching in time or sweeping in space, okay, that there is an equivalence, okay, that we are fine. Is that okay? Right. So that's the end of the aside. That we'll get back to where we were. That's the end of that aside. We'll get back to where we were. What we are talking about now is how much dissipation can we add. We saw that if you add too much dissipation, if you add way too much dissipation, the stability condition changes, right, and the stability condition gets actually worse. The time steps that you have to take will get much smaller. So you have to be very careful whether how much dissipation. You may be tempted to add a lot of artificial dissipation. That does not quite work. The second thing is, if you add a lot of the artificial dissipation that you add right now, the way we are adding it, you could say we are adding it explicitly, right, we are adding it at the current time level. The way you are adding the artificial dissipation actually contaminates the solution, right. So if you say, hey, wait a minute, I am not actually solving the equation that I set out to solve, anyway I am solving the modified equation, I am going to add artificial dissipation, that is one argument. The other thing is, look, you know you are solving the modified equation, instead of improving it so that the modified equation gets closer to the actual equation, why are you making it worse, right, that is a counter argument that you can get, right. So we have to be a bit careful how you handle this, but you have to have an awareness that whether you like it or not, when you solve the problem there is numerical dissipation that is showing up, because the modified equation is not the same as the original equation. So you have to have an awareness as to what it is, right. The second thing is, if you are going to add something to it, you have to add it carefully, right. Okay, let me try to come to this problem from a different direction. Let me try to come to this problem from a different direction. Okay, what if you had dou u dou t plus a dou u dou x equals 0, and I did not add, I have been writing this and I did not do that. Or what if you had, instead of a dou u dou x, you had either a as a function or you had something else, you had some u, right. The kind of equation we are used to in fluid mechanics would be something like this. Where u is the solution and therefore you do not know what it is, right, you do not know what it is beforehand, a priori you do not know what is the value of u. Okay, so what if you had this situation? How do you ensure that you are doing FTBS? How do you ensure that you are doing FTBS, right? We will look at this equation in greater detail a little later, but right now I am using it just for motivation. How do you ensure that you are doing FTBS, or I am sorry, how do you make sure that you are using upwinding, right? It is not so much FTBS, but how do you make sure that you are doing upwinding? Right, if you do not know what the sign is, you have a scheme, you do not know what the sign is, how would we make sure that we are doing FTBS? So there are different ways by which you could do it. Of course you could have a if then kind of a discretization, right. So the algorithm then becomes, it is a true algorithm. You turn around and say, if a is greater than 0, use backward space, if a is less than 0, right, use forward space, that is a possibility. A equals 0, I do not know, right. A equals 0 of course does something to this particular equation, so life becomes easier. A equals 0 can be a headache, right. Again we will see what that headache is at a later time. So the other possibility is that you can ask the question, is there a way for us to create a switch, an automatic mechanism, so that I do not have this conditional statement, right, possibility. So the question is, what is that quantity and what is this quantity. So if I divide this by 2, right. So if A is positive, this would be 0, right, and that will be A. If A is negative, this is going to be 0 and this would be A, right, would be A, fine. So now we have something that looks like a switch, something that's 0 1. So you could then turn around and say that UPQ plus 1. The objective here is I want you to see where we started off with. We started off Laplace equation, central differences, we tried it out, various things, some things worked, some things didn't work. How do you develop these algorithms? What is the way by which we are groping around, but as we get along you get better at it, right, and there are lots of little tools that you can use to construct algorithms. You have to get an idea as to how these things happen. So this is UPQ. I seem to have automatically shifted to a superscript, it does not matter, right, minus A plus mod A by 2 delta t by delta x into, what do you want here, UPQ minus UP minus 1Q Q, thank you, minus A minus mod A UP plus 1Q minus UPQ. Is that fine? So this would do it, this would automatically switch. It's one way to do it. So automatically switch. You don't have the conditional statements, but then you are doing a lot of work, right. You don't have the conditional statements, you eliminated the conditional statements, but you are doing a lot of work. You are going to evaluate these terms independent of whether that's 0 or not, right. You are going to add them all up and throw them away, and you are going to add them all up, and it may turn out that what you have, fortunately here you are not going to end up with round off error because they are identical, right, but these kinds of algorithms you have to be a bit careful. So you are going to calculate all of this and just chuck it because that happens to be 0. What is the other possibility? What is the other possibility? In the last class we saw something. What is the other possibility? What was the difference between central difference and forward difference or backward difference? You remember? I want to add something to this. What was the difference between central difference and backward space, or central space and backward space? Do you remember? Second derivative, but the coefficient is very important. Okay. So it is something like, I will add mod A because we do not know the sign of A. I will add mod A, right, delta x by 2 dou squared, that is, I hope I do not want the continuous thing, I want the UP plus 1Q minus 2 UPQ. You can go check this from your last class, plus UP minus 1Q divided by delta x. Is that okay? Is that fine? Okay, that is fine. Why did I do mod A here? I do not know the sign. I want you to check that both FTCS and FTBS, what is the difference between FTCS minus FTBS, FTCS minus FTFS, okay, and see what you get. So if you add this quantity, what is it going to do? It is going to convert the central difference to backward space, you understand, and by taking this sign out of the game, I have essentially made sure that whether it is forward difference or whether this is positive or negative, that is going to cancel out. You can just try it out and see, okay, and it will always be upwinding. That is another way to do it. You add the right kind of artificial dissipation, right, you add the right kind of artificial dissipation. Of course, from a stability point of view, what we are talking about earlier, I can't afford to have this A to be negative, that is pretty obvious, that is mu2 negative, right, that is mu2 negative. Does that make sense? That is mu2, if A is negative, that means mu2 is negative, it is going to diverge, right. So it is pretty clear that it has to be modulus away. That, see, there are different clues that we have as to why we are doing what we do. Either you can do it from here to see what is the correction term that I have to do in order to change a central difference scheme to a upwinding scheme, or you can look at it from the modified equation that we have got and say, oh, the coefficient has to be positive. Is that fine, everyone? So there is a way, there are clear cut ways by which you can determine what happens when you add a specific term, but the addition of this term doesn't, so it does not eliminate the second derivative term. The addition of this term only converts the central difference scheme to a one-sided difference, one-sided first order scheme. So we lost the order, of the scheme, okay. Are there any questions? So while we are at this, so we have seen that you can do so we have FTCS, FTBS, FTFS, right. We have to use either FTBS or FTFS depending on which way the stream is flowing. So it is better to do FTCS, a centered scheme. See, this is one way to look at it, one argument, and just add something to it so that it becomes upwind biased, or the other thing is to say that you do upwinding directly, right. You can get, so whether you are doing upwinding, so I would say if you are doing this, you are also doing upwinding. It is very clear, if you are doing this, you are also doing upwinding, right. So there is no sense getting into an argument as to whether you are doing central differences or up. It is just a matter of, in order for the error to decay, I am going to have dissipation, and in order to get the dissipation, I need to do something, okay. So there is no sense getting into an argument as to whether you are doing central differences or, but the minute you say it is FTCS plus a correction term, then we can ask the question, can I eliminate the higher order terms and get a more accurate scheme? That is a different story, right. We will look at that, as I said, when I do the demo, okay. Now that we have done this, I know in the beginning of the class I said I am not going to do a survey of a lot of schemes and so on, but I am going to do a few schemes now, just to show you, just to go on with this philosophy of how do these schemes evolve, how do we develop these schemes, right, and I will get you to a point where you should be, if you really want, right, if you go out, look at all the schemes that are out there and you say no, I do not like this, I have a better idea, you should be able to come out with something on your own. Is that fine? Okay. So we come here, what we will do is, and all of these, as I said, we have clues for these things from what we have done so far. We have clues for these things from what we have done so far. So earlier when we derived modified equation, what had I suggested? When we did modified equation, what did we do? We expanded using Taylor series, and we substituted for individual terms in Taylor series. Okay, then you can ask the question, why not develop a scheme using Taylor series? This is a classical technique, using Taylor series to solve differential equation. That is, if you have UP q plus 1, I guess maybe I will stick to the subscript, is UPQ plus, let us do Taylor series, delta T dou U dou T at the point PQ plus delta T squared by 2 factorial dou squared U dou T squared at the point PQ, and so on, fine. When we did the modified equation, of course we wrote the right hand side, but here I am going to stop at this point. I say, wait a minute, why go there at all? We already have a trick. What is dou u dou t? Dou u dou t is minus a dou u dou x. Again I am back to a greater than 0, that situation where a is greater than 0. And what is dou squared u dou t squared? A squared dou squared u dou x squared. Substitute back. UPQ plus 1 is UPQ plus delta t A dou u dou x is UP plus 1q minus UP minus 1q by 2 delta x minus sign, I do not know, I always forget that minus sign, okay, fine, plus a squared delta t squared by 2 delta x squared. I do the open bracket here, but I am going to write it here. What is it? Or maybe I will write it in the bottom. A squared delta t squared by 2 delta x squared UP plus 1q minus 2 UPQ plus UP minus 1 q. How is that? We just cooked up a scheme. This is called the Laxman scheme. Laxman scheme, right? All you just basically do is you just go through, do a Taylor series expansion. Classically it is solution to differential equations using Taylor series. It was normally done with ODEs. I guess this application to PDs, they get the credit for it, okay. So here you have it, FTCS there, FTCS there. So this would be sigma, and that would be sigma squared by 2. Fine, and the scheme comes with its dissipation added, right. You can try out, you can go through, do the stability analysis for this. I am not going to do this anymore, right. These I leave as exercise. You can try out the stability analysis for it. You can find out the modified equation and see what is the nature of the modified equation, right. You can try to find out what is the nature of the modified equation. Is that fine, everyone? Okay. What else? I am just going to now in a freewheeling fashion connect all the bits and pieces that we have done to see whether we can come up with other schemes, that is all, right. I am just going to do a few of these before we sort of end this whole thing of linear wave equation, right, okay. So I am going to just sort of try around. There is something called a two-step Laxman method. They do the following. I will draw the stencil in this case simply because I am actually drawing grid lines, simply because it is easier to understand with the grid lines. So this is p plus 1, p minus 1, p plus 1 at time level q, that is q plus 1. I seem to have drawn a line in between. I will also draw another line in between here, lots of extra lines, right. So that is, this is a point PQ plus 1 basically, that is what we want. I am going to do this in 2 steps. I am going to do this 2 different ways, right. I will tell you what is the 2-step scheme, final 2-step scheme. So what we can do is, you have the value here, you have the value here. If you had this in between value, you could do FTCS and find that. So humor me, I will call that p plus half, right. I know, I mean we were counting, it is integers, but we will call it p plus half, p minus half, good. Even with counting I have to make sure I get the sign right, today is my day for negative signs. Anyway, p minus half. So then this would be P minus half. Well, you would expect that would be Q plus half, right. So you can see that if there was a way by which I could use FTCS to find that, and a way by which I could use FTCS to find that, then I could repeat the process and use FTCS between these two to find that. Is that fine? Okay. Two-step process. The process what I just described now is not the two-step Laxman process, it is a two-step process. So let me write that over first and then I will tell you what is the improvement. So you can say UP minus half, maybe I will go back to superscripts here, Q plus half equals UP minus half Q minus A delta T by delta X UP minus UP minus 1, these are all at Q. Is that fine, everyone? How do I find that UP minus half Q? Give me a suggestion. Take the average. So I can take the average UP minus half Q is UP plus UP minus 1 divided by 2, fine. So in a similar fashion UP plus half Q, well it would be the same, I mean, so obviously you are going to find this value using these two, right. For each of these intervals you do that. So I will go directly to UP Q plus 1. So here is the first suggestion, UP Q plus half minus A delta T by delta X, we are assuming delta X's are equal everywhere, UP plus half Q minus UP minus half Q. Does that make sense? And any time to find this intermediate value, if you do not know it, take the average of the neighbors. Okay, everyone, it is fine. So do you expect this to be stable using FTCS? You expect it to be stable, it should be unstable. Before you start the stability analysis, you first predict what you expect it to be and see whether you get it, right. And in order to do the stability analysis, you have UPQ plus 1. Remember, you have to get this in terms of right hand side has to be all UPQs, which basically means that you substitute for the P minus halves in terms of P's and P plus 1, you understand, eliminate all the halves, that is the easiest way to do it. Just make the substitutions, eliminate all the halves, so that you finally get UPQ plus 1 in terms of UPQs. Okay, take the ratio and you can do the stability analysis, fine. This is a two-step method. The two-step Laxman method, you stop at this point and you say, wait a minute, there is something here. Why bother with taking FTCS here again? I have the value here. If I take a time derivative across this, I am taking a central difference at this point. I do FTCS to get that, I am sorry, FTCS to get that, I do FTCS to get this point, FTCS to get that point. Here I can do central time, I can actually do central time, I can get a higher order accuracy in time, I can do a central time, is that fine? I can do CTCS, that means the second step, instead of using this in the two-step Laxman method, you would write UPQ plus 1 is UPQ minus the rest of the stuff. Central difference in time, central difference in space. Okay, one of the reasons why I do not do this is it can get dreary. right, it can get tiresome. I am just putting up indices out there, right, I can already see it on your faces. It can wear you out. Okay, this is the 2-step Laxman Trough method. It is done in 2 steps. First you get to q plus half and then you do the full thing, full delta t, fine. Okay, I did this so that you are aware that you don't have to do it, it does not have to be done in one step, you can do it in multiple steps. The time integration can be done in multiple steps, and there are a whole class of Runge-Kutta schemes and so on where the time integration is actually done in multiple steps. So there are multi-step methods, right, just so that you are aware of it. A third thing that we did right back at the beginning when we were doing finite differences, what have we done so far? Amongst the various things, we have done FTCS, we have done BTCS, and of course we have done a lot of other stuff, but I am more interested in FTCS and BTCS. Before we derived finite differences using Taylor series, we did it for forward difference and backward difference. Do you remember the first time I introduced central difference, what I did? You remember what I did? I took the average of the forward difference and backward difference, right. I looked at the truncation error term for forward difference and backward difference and said, wait a minute, these are the same magnitude but opposite sign, why don't I take the average? I have forward times central space, backward times central space, why don't I take the average? Why don't I take a combination of these two? You understand, right? Or better still, I can take a weighted average. Not why just average? Now we are into things like SOR and things. So why not just why not a weighted average? Why not a theta times FTCS plus a 1 minus theta times BTCS? That sounds vague, right? Theta equals half would be an average. Theta equals half would be an average. How do we do this? Theta times UPQ plus 1 equals theta times UPQ minus theta sigma by 2 UP plus 1 minus UP minus 1. What is BTCS? 1 minus theta times what was BTCS? Sigma by 2 UP plus 1 Q plus 1 minus UP minus 1 Q plus 1 plus UPQ plus 1 equals UPQ. Is everybody with me? Is that fine? Okay. So add them up, we will see what we get. If you add them up, what do you get? There is a 1 minus theta UPQ plus 1, just to point out this always happens, a theta UPQ plus 1, so the theta will go away, right. So you get a, from here, a minus sigma by 2 UP minus 1 Q plus 1 plus UP Q plus 1 plus sigma by 2 UP plus 1 Q plus 1 equals, again as I pointed out, the theta and minus theta will cancel, UPQ minus theta sigma by 2 UP plus 1 Q minus UP minus 1 Q. I lost some 1 minus theta somewhere. There should be a I hope that is not too messy. Fine, fine. And theta equals half, theta equals half, theta equals half, you get a very famous technique called the Crank-Nicholson technique. But here you would have to solve a system of equations, but clearly you can take various values of theta, right, clearly you can take various values of theta. I would suggest that you try to do the stability analysis for this, you try to do the stability analysis for the two-step Laxman-Trough method. All of these schemes, p plus 1, p plus 1, p minus 1, q plus 1, both of these schemes represent the differential equation, approximate the differential equation at the midpoint. Both of these schemes represent or approximate the differential equation at the midpoint. Fine, okay. Okay, so I will see you in the next class. Thank you.